Okay, what I want to look at right now is an example of free fall acceleration. So let's imagine that we're standing on the top of a cliff and we have a rock or something that we're just going to drop. All right? So I want to think about how speed changes as this rock falls. All right? So what I would say, the moment we release this rock, we are at time, so our delta t is 0. No time has passed. It's the moment that we drop it. Well, if I'm dropping it, it was essentially at rest when I let it go. And so what would you say your velocity is at this location, time 0, the moment I drop the rock? Well, it's going to be, if you ever saw the Coyote and Roadrunner, this is like when the coyote ran off the edge of the cliff, and that moment as he ran off, he wasn't moving downward at all. So we would say that our initial velocity, up and down at least, is 0 meters per second. Okay? Now, the rock is, of course, going to begin to fall because gravity's pulling on it. And so let's just say that that rock is in this location after 1 second has passed. My guy here is totally out of scale, but let's just say 1 second has passed as this thing falls. Well, what we will see is that after 1 second, our new velocity at 1 second is going to now be equal to approximately 10 meters per second. AP Physics, we're usually going to use 9.8. I'm simplifying just to make the math a little easier. Okay? So after 1 second, the velocity of this rock is now 10 meters per second. And I'm going to say negative 10, since usually if it's moving in the downward direction, we call that the negative direction. Upward would be the positive direction. Okay? Now, after 2 seconds, our rock's going to be about in this position. So our new delta t is going to be 2 seconds. And if we could measure that velocity at that moment in time, we would find that our velocity after 2 seconds is going to be negative 20 meters per second. Okay? If I let another second go by, so my delta t now is going to be 3 seconds. My new velocity at this point in time is going to be negative 30 meters per second. Okay? Now I could continue on, but I kind of ran out of space here. What you'll notice is, number one, as time goes on, the space between these positions gets bigger and bigger and bigger as it falls. It goes through more space each second because I'm seeing a velocity change here. It is accelerating. All right? This rock is accelerating downward because gravity keeps pulling on it. And so it's going to continue to speed up. It's going to continue to accelerate. Okay? In the absence of any kind of air resistance, this is just going to keep going faster and faster and faster. What do you think it would be after 4 seconds? 4 seconds of falling. Well, if you look at the pattern here, after 1 second it had increased by 10 meters per second. After 2 seconds it had increased by another 10 meters per second, or 20 meters per second total from the beginning. After the 3rd second, you add on another negative 10 meters per second. What do you think it would be at 4 seconds if it continued to fall? Well, if you look at the pattern, it should be negative 40 meters per second. All right? So what we're seeing is for each of these 1 second intervals, I'm going to get a change in velocity. Now, I want you guys to look at this. You should be able to tell me what that change in velocity is for each of these intervals. And if I did if it went to 40 on the next one, I'd get the same thing. What's my change in velocity for each second here? My change in velocity is negative 10 meters per second. All right? So the point I want to make to you guys here is that when you look at the way gravity works, all right, when you look at the way that gravity works, it works the same all the time. I'm going to slide myself right over here. It works the same every single time. By that I mean this object is going to speed up by -10 meters per second each second. So I would say that gravitational acceleration is always -10 meters per second squared. All right, this is a constant, you guys. On Earth, because of the gravitational force that's acting on every object, we always see accelerations that are right about 10 meters per second squared. Why do we make it negative? Because it's always downward. Gravitational acceleration never pushes us off the planet, thankfully. It always pulls us back down. And it will not change. It doesn't even matter how much mass that the object that you're dropping has. All right, it's always the same. This acceleration is always the same. We could label this, if we're doing a calculation, we could label this as A for acceleration. But very commonly, we also show gravitational acceleration with a lowercase g. All right? And usually when we call it g, the other thing that we're going to do is instead of calling it negative, we make it positive. So if you ever see an equation that's got a g in it, they're talking about gravitational acceleration. Okay? So this is the way that falling objects always work. It doesn't change. This acceleration is the same no matter how much mass you have. And also, it generally works all the way up into the atmosphere. So if you're on top of a mountain, your gravitational acceleration is going to be slightly lower, but it's going to be extremely close to 10. Okay? All right, so that is the acceleration that drives free fall acceleration. So the accelerations that I just showed you, that -10 meters per second squared, gravitational acceleration, that's going to work as long as we are in free fall acceleration. Remember, what that means is all you have pulling you down is gravity. There is no such thing in our atmosphere, though. We always have air resistance. So if you think about it, instead of speeding up at 10 meters per second squared, that rate of acceleration, since we really do have air, would it be a little more than 10 or a little less than 10 if you have air resistance keeping you from falling through the air? So you can imagine that if you're falling, what air resistance would be is, as I was falling through the air, there's molecules of air that I have to move through. And my body has to shove those molecules out of the way before it can occupy the space that air was in. That's where air resistance comes from. So what would happen if we did have air resistance? Well, air resistance is a force that's acting upward as I fall. So without it, I fall as though there was no air, as you guys saw in the video when we talked about free fall acceleration. But with it, that's actually going to slow me down. I won't quite accelerate at 10 meters per second squared because that force is upward. And the faster I move, the more air molecules I got to shove out of the way, and the slower I'm going to accelerate. So we're going to watch a quick video here of a guy named Felix Baumgartner. He actually, a few years ago, essentially jumped from outer space. He parachuted to Earth from outer space. Now, why are we going to watch this? Well, this is what true free fall acceleration would look like. I think he jumped from like 100,000 or 120,000 feet. Up there, the air is so thin that it approximates having no air resistance since there's no air.
release.
If you're scared, walk away. 'Cause there's no need to feel ashamed. Yeah, we all feel the same. Where's your passion? Where's your fire
All right, now the whole road is looking on. I'm going over.
Jumper away. Speed 725. Showing Felix in a stable descent. And Felix is back to run safely, the new world record holder.
All right, guys, so we can use the equation that we already have for acceleration to help us figure out a couple of other things. So for instance, let's say that you have a skydiver and he's jumped out of an airplane and he's freaking out a little bit and he wants to know how fast is he actually falling downward. Well, you'll see that there's only a few things you really have to know in order to determine that very thing. Now, if he wants to know how fast he's falling, what he really is asking for here is, what in the heck is my VF? What's my velocity at that point in time? And that could be here. It could be, hopefully it's not, when you get all the way down to the ground. Hopefully it's before that. But you'll see that by using this formula, we can actually simply solve for VF. And this is a pretty easy new equation, although it's really just a little bit of algebra on this one. So if I solve this equation for VF, the first thing that I would want to do is get rid of delta t. So I want to get rid of that. At least I want to get it out of the denominator here, because I make mistakes when I use fractions. So I get rid of the fractions as quickly as I can. If I rewrite this equation, I get a delta t on the left. And the t is now gone, so I have VF minus a VI. Okay? And if we want to solve for VF, we just add VI to both sides. This gives us, these canceling, gives us a new equation, which is essentially VF equals VI plus A times delta t. All right? This is a new formula. If you guys have your comp books, you should be putting this in that last page in the comp book. You should be putting this formula in there. It really is the same as this. We just did some algebra so that if you're on a quiz or a test, you don't have to immediately remember how to do all the math and then make a mistake because you're stressed out. Okay? By the way, typically on exams, you do not have to memorize formulas. You're allowed a 3x5 card that has the formulas on them. Okay? So don't worry yourself about memorizing formulas. I've never really understood why a lot of people in math make you do this. If I haven't used a formula in a couple of weeks, I'm going to look it up before I use it because my memory may fail me. So what's important is you know how and when to use the formula, not that you know what the formula is itself. Okay? So this particular formula will allow us to solve for what this person's velocity would be at any time, as long as I know how long they've been falling. Okay, if I simply know time. If you think about it, if you were in this airplane and it was flying level, your vertical velocity in the beginning, when you first jumped, would be 0. You're not moving up and you're not moving down. So your initial velocity in the vertical direction, at least, VI would be 0. And this gets even simpler if VI goes away. If that's 0, this becomes, so what I'll say is from rest, all right, from rest, this would simply become VF equals A delta t, since the VI term would be 0. Okay, so if this is an object that's falling from rest, this is really, really pretty simple. Okay, if you know what free fall acceleration is, and you know how long it's been falling, you got the velocity. All right, lastly on this lesson, I want to talk about something that's not quite free fall. I want you to imagine that you've got a ball, and this is one of the sadder scenes you'll ever see, is a kid who wants to play baseball and has no one to play catch with. And so he's sitting there and he's throwing the ball up in the air and then catching it. Sad, really. But let's just say that instead of allowing the ball to simply fall from rest, all right, instead of allowing just that free fall to occur, that instead I'm taking the ball and instead of just dropping it, I'm tossing it upward. So I'm tossing it upward like so, and then it's coming back down. So what happens here in terms of velocity? Well, let's diagram this a little bit. I will put someone here on the ground, and they're tossing a ball upward, and that ball's going to go up, 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 and then it's going to come back down. All right? It's really a horrible line, but you get what I'm saying. So let's just say, for argument's sake, that at time 0, all right, at time 0, the moment the ball leaves his hand, this ball, instead of dropping from 0 velocity, it actually has a velocity. Let's say that my VI is, I'll say 25 meters per second. Okay? And because it's going upward, because they're tossing the ball upward, I would say that not only is it 25, but it is positive 25, since upward motion is positive and downward motion is negative. Okay? So the moment it leaves the person's hand, it's traveling upward at 25 meters per second in the upward direction. Now, does gravity act on it? Is gravity acting on that ball after it leaves his hand? Gravity always acts as long as you're on Earth. Oh, and if you're on another planet, by the way, it still acts. It just acts differently because of how big the mass of Earth is versus other objects. Okay? So here on Earth, the ball's thrown upward. It has a velocity of 25 meters per second. Okay? Now, the ball's going to continue to fly up. Now, you guys have, I'm sure, thrown stuff in the air. What happens to, if it leaves my hand, what happens, let me get something you can see better. As it leaves my hand, what's going to happen to its motion as it continues to travel upward? Is it constant? Do you have a constant velocity as it goes up? You don't, all right? Because gravity's trying to pull back down on it, it's actually slowing down as it goes upward. At what rate would it slow down? Well, we already know what that is. We know that our acceleration is negative 10 meters per second squared. So that means each second that it goes upward, you're going to have an acceleration of negative 10 meters per second squared. So after 1 second, let's just say that the ball is right here. So delta t equals 1. If our speed is changing by negative 10 meters for each second, then between this location and this location, our speed must have changed. I mean, that was 1 second's time. Our speed must have changed by negative 10 meters per second. So if it started at 25 right here, I'm going to put velocity at time 1. That's not an I, it's a 1. What would my velocity be at that point? Well, if I was at 25 and I know that each second that it flies, it's going to change by negative 10 meters per second, I must be at positive 15 meters per second. All right, it's changed. The change in velocity that you had is negative 10 meters per second. Okay? What about when 2 seconds have gone by? So we say our delta t is 2 seconds. What would our time be, or excuse me, our velocity be at time 2? Well, remember, each second, here's 1 more second's time, you're going to have the exact same change. So if I was at positive 15 at this moment, I'm going to be, it'd be positive 15 minus 10. This is going to be positive 5 meters per second at this new location. So I know the ball has not gotten to its peak yet. All right? It's still moving upward because this is positive. All right? What about at time equals 3 seconds? Now, I'm going to draw it on this side, and I think you'll see why in a minute. So our delta t is 3 seconds. If each second were changing by negative 10, okay, how much change would we see after 3 seconds? Well, it'd be negative 10 for the first second, another negative 10 for the second second, so we change by negative 20, excuse me. By the third second, the change that we've undergone is going to be negative 30. So if we started at positive 25, what's our speed if our change is negative 30? Well, our new velocity here, our v3, should be negative 5 meters per second. Excuse me, not squared, that's just meters per second. Okay? So, is the ball still on the way up if this is our velocity after 3 seconds? Because it's negative, we know the ball's on the way back down. So that ball is now going to be in this location, all right, at 3 seconds. So sometime between the second second and the third second, it got to its peak and started back down. Okay? Now, what about at time 4? So after 4 seconds since it left the person's hand, okay, now we had a 1 second pass between this location and wherever the fourth is. So that means I need to change it by another negative 10. Each second it's going to change by negative 10 meters per second. So if I was at negative 5, my new velocity at time 4, okay, our new velocity at time 4 should be negative 10 added to this. So this would be negative 15 meters per second. So that's going to be in the same location basically as it was on the way up. All right? After 5 seconds. I know there's a lot of numbers and stuff, but hopefully you're following along. At 5 seconds, what's our change? Between 4 and 5, what's our change that's going to occur in that velocity? Well, gravity doesn't change. It's always the same. It's going to be another negative 10 meters per second for each second that it moves. So if I was at negative 15, I'm now back to negative 25 meters per second. And where would the ball be? It would be in the exact same location it was when it left his hand. He'd be catching. All right, so what you guys should notice here, each 1 second interval, you had a negative 10 change in velocity all the way through there. Now, this leads to, you may have heard this before, you should never shoot a gun in the air because whatever the speed that the bullet leaves the gun, whatever that speed is, that same speed is what you're going to get when it comes back down and hits the ground. Theoretically, that would be true, but the truth is, it doesn't work like that. That bullet's going to get all the way up to the top of the flight at this point right here, and it stops for a moment. And then it's going to start to fall back down, just like I labeled here, except now it's no longer spinning in a nice aerodynamic shape and spin. It's going to start to tumble. So it doesn't get that fast. I think I saw Mythbusters once, and they dropped a penny from the Empire State Building in New York because the idea was it would be moving so fast that it would kill somebody if it hit them in the head. Well, what they actually found out was it never got any faster than about 40 miles per hour. So they basically got a nail gun and they rigged it up to shoot pennies at 40 miles an hour, and then one of them shot it at their hand. It hurt, but it didn't kill them. Anyways, this is the way you can see that these rules work. It doesn't matter whether you're going up or down. Why did you slow down on the way up? Because your velocity was upward, but gravitational acceleration is always downward. Because they were in opposition to each other, the change in velocity that you're going to see is going to cause a decrease in that upward velocity. Okay? Because they're in opposite directions, it's going to be slowing down. When you got to the peak, though, and you started to fall back down, now your velocity, -5, for instance, is in the same direction as your acceleration, -10. They're both negative, so that means that speed should increase as you fall. All right? So this is the way that it's going to work. It really doesn't matter whether it's a free fall or something that you've thrown up in the air. Your acceleration is always going to be the same. Gravity always points downward. All right, AP Physics. This example is for you as we talk about free fall acceleration and some of the problems that we may see involving it. So this one says that Derek strikes a volleyball so that it leaves his hand at 12 meters per second upward. How long will it take to reach its peak? So again, what we're saying here is that Derek's going to be standing on the floor. He is going to strike the volleyball, and the volleyball is going to go up and then back down. And we want to know how long is it going to be before it's at that location. So what I want to do then is I want to start identifying some variables. Now remember, I told you guys that when we do these problems, the first thing you want to do is read for understanding. You want to understand the scenario as it's playing out. And so diagrams often help with that. Let's think about what we know. We know that the volleyball leaves his hand at 12 meters per second in the upward direction. So this is clearly a velocity. I know that because it's got meters per second. The question is it VI or VF? Well, it was the initial velocity with which he hit it. So this is VI. We know that VI is 12 meters per second. And I'm going to go ahead and very overtly say that that's positive, that's upward. Okay? Now, the other variables that we've talked about so far, we've also talked about VF, okay? We've talked about A, and we've talked about delta T. These are all variables that we've been discussing. I'm just going to write them down, and let's figure out how many of these we know. Now, do I know what VF is, the velocity at this point in the ball's flight? Well, this is a special location. When you look at the peak, you're going upward. We know that we started with an initial velocity of positive 12 meters per second. What's happening to that velocity, though, as you go upward? Because gravity's pulling down as this ball's trying to go upward. It's slowing, 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 slowing. And what can you say about this location? Well, up to that location, your velocity was always greater than 0. All right, it was positive. It was greater than 0. After it gets to this point and starts back down, what I would say is this entire space, your velocity, is always less than 0. It's negative. So what must the velocity be here if this is the location where you change from being positive to being negative? Well, what's right in between positive and negative? We would say that our velocity in this location, and we're going to call it VF, because in terms of our question, we don't care what happens after this, but we're going to say that at that location, our VF is 0. Just that split moment that it gets to that location and then turns around, our VF is 0. So even though it didn't come right out and say it in this question, we know that for any ball that's going up and coming back down at the peak, it's always going to be 0. Do we know what A is? That's just gravitational acceleration. Now for you guys, instead of using 10, we're instead going to call this 9.8 meters per second squared. All right? We usually just round to 10 if we're kind of doing some calculations in our head. But we want a more precise number here. How about time? Well, if you read the question, how long will it take? They're asking me for delta t. All right. So we have our formulas here. We can either use this one, Vf equals Vi plus a delta t, or use the acceleration formula that this came from, which is a equals Vf minus Vi over delta t. And our objective here is to solve for delta t. So when we pick formulas, we could pick either one of these two. They both have delta t in them, and we know everything else. So I could use either or. I'm going to use the one that has the easiest math. And for me, that would be the bottom one. All I would do to this one right here to solve for delta t is I don't want to solve for 1 over delta t. I need to get delta t out of the denominator. So I would basically multiply both sides by delta t, okay? But once I get the delta t over here, I need to get rid of a. So I'm also going to divide by a. All right? Now, what is this going to do for me? Well, essentially, I'm going to cancel the delta t. The a stays in the denominator. And over here, I'm going to cancel a, and I'm left with delta t. So delta t equals Vf minus Vi over a. The net result is when you do this algebra, you guys, you just switch places between this and the a. The a moves down here, the delta t moves up there, and you get this. Now, at this point, I can go ahead and plug in. First thing I need to do, though, before I plug in is check my units. And what I see, let me go ahead and put meters per second there. All the distances in these units are meters. All of the times are seconds. We can go ahead and plug in. Our Vf is 0. Our Vi was positive 12. And our value for A is negative 9.8 meters per second squared. Okay? So what we're going to do is we're going to divide a negative 12 by negative 9.8. That gives me a positive answer. It better give me a positive answer because time can't be negative. So if you ever get a negative time, you probably did something wrong with the sign or with algebra. So this is going to be 12 divided by 9.8. What do you get? Go ahead and calculate that for me, Dan. You should get a number that's right around 1.2 seconds. It should be just a little bit bigger than that. So 12 divided by 9.8. 1.22. I'm really only allowed 2 sig figs because the 12 is the only number they gave me. So we're going to round 1.22 to simply 1.2. If I think about my unit, I'm dividing meters per second by meters per second squared. So in essence, the meters cancel. This seconds cancels out one of those. So I'm left with a unit that is 1 over seconds. The unit of the denominator of the denominator becomes the unit of the numerator. If you divide by a fraction, you multiply by its reciprocal. So this comes out to seconds, which means my algebra was probably correct. This is your answer right here. Basically, it's going to take, if you launch from that speed, it will take 1.2 seconds to reach the peak. And you can do this for any position, you guys, in the flight if you know what both velocities are. Okay? I'm going to stop right there.